All right, guys, so this is going to be the last question for this morning's lesson, okay? So we're going to I decided to break up the videos just so you guys had an example of just the cylinder and just the cone, okay? So we're going to look at the cone here. Okay, and the interesting with the cone, the problem with the cone is you got two things going on at once, right? As we increase the height, right? Like as the water level in the here, I'll draw a picture. So we're gonna draw our cone. This is the problem with these questions. This is why they're a little bit more complicated. As the water level in the cone rises, so as dH by dt increases, we also have the fact that the radius dr by dt also increases. Okay, and so this is what makes, unless you're provided with this information, that's what makes this question a little bit more difficult, is because you've got two things changing at the same time, right? So you got to ask yourself, okay, well, how do I deal with a situation like this, right? Because you're not always going to have all this information, right? We know how much water is flowing into the tank at any given time, right? That's given to us in the question. We could probably also write some other things down here, like the radius here at the top has a 10 meters, right? And the height is going to equal 24 meters, top to bottom, right? And we know it's how its volume's changing. So the other thing we want to know is, here, I'll get rid of some of these, is when the water is 16 meters high, how is this all, what's going on when the water is 16 meters high? That's our question. Okay, cones are quite tricky. So, but let's start with the fact that we can represent a cone in a way, right? And we know that, we're talking about how the volume is changing. So let's represent this situation with the volume of a cone. Well, we know the volume of a cone is going to be equal to 1/3 pi r squared h. Okay. Now, again, initially we might think, okay, well, if I could, treat this, leave the 1/3 and the pi alone and treat this as your f of x function and your g of x function, you could apply product rule and derive this implicitly, but then you're going to get this dr by dt thing in there, right? And it doesn't tell us how that is changing with respect to time. It only tells us about the dh dt. That's what makes this tricky. So if you were to do it that way, you'd end up in a situation where you don't know how the radius is changing. You wouldn't be able to finish off this question. But there is a workaround here. Okay? The workaround is what if we could take the ratio of, how is something changing? How is this radius changing relative to the height, right? Like if we could write the radius in terms of the height, then our problems would be solved. Okay, well, let's take a look here. Let's take a look at what we physically got here with these cones, and this is how you would tackle this. We're going to have a series. This is your R. We'll call this, I don't know, whatever it is, R, and we have H. Right? Both of this is 10, and this is 24. We get, if you guys look here, a triangle. Well, then we could go, okay, well, what about the radius, when the radius, what's the radius? We'll call this R naught. When H is equal to 16. Well, hopefully this looks familiar, okay? You could treat this like a similar triangles question, right? So you set up a little ratio. You say, okay, well, we can say R naught over H naught, right? We could say R naught being the thing that we were looking for, sorry. R, obviously, because it's not labeled. R naught over H naught, we'll call this H naught, has to equal R over H. So let's plug in our numbers. Okay, well, R naught we don't know. That's going to be over 16 is equal to 10 over 24. Okay, we could do it this way, but what if this is a very like one radius argument. Okay, what if we wanted to find R naught with respect to any H, any water level in here, right? Because ultimately that's what we want to know, right? We want to find, you know, what's the radius at any height H in here, right? So let's leave this as H and write R naught in terms of, this is going to be our shared variable, if you will. Okay, and we can say, okay, well, R naught is going to equal to 10H over 24. This allows us to find what the radius would be for any particular height of water level. Okay, so we can use this. Hopefully you guys can see that. Yeah, that's okay. Okay, we can use this and plug it in here. And watch what happens. We can rewrite our volume equation now. Volume is going to equal 1/3 pi. Well, what's going on here? Well, we get 10H over 24 squared. Okay. I suppose, sorry, just to make our math or our lives a little bit easier, we could reduce this 10 over 24 to be 5 over 12H. Okay. I'll use this instead because the numbers are a little bit smaller. It makes squaring everything kind of nicer. Okay, so we'll do that. 5H over 12. And don't forget to multiply by the H. Okay, and this is H over 1. So what does this turn into? Well, V equals 1/3 pi 25 H squared over 144. Right? And then you can multiply the H in. Now that you've done this exponent work, you can multiply the H in, and we're going to get, I'll write it out so we all make sense, okay? Times H. I won't skip any steps. Okay? You could even say, okay, well, V is going to equal, I can multiply the 1/3 into this bracket now. You could even say we're going to get 25 pi H cubed over 2, no, it's going to be more than that, 432. Okay? So, we've gone some, let's just recap. We'll take a little pause here. And we'll recap what we did before we do anything else. We represented the question accordingly, just like normal. That was the first thing. Then we came to the realization that we're going to have, the radius is going to be changing at the same time that the height is changing, and we don't like that, right? So we came to the realization that, okay, well, maybe I can write the radius in terms of the height. Okay, but let's not think so like so we're not close-minded, but small scale. Let's not think small scale. Let's write the radius in terms of the height. For if I were able to say if the height's 20, I could plug in the height to be 20. If it's 16, it's 16. If it's 10, it's 10, right? Let's do that instead of being so short-sighted in the sense that, like, if I could plug in the 16 here and then find what R naught would be equal to. Okay, that's a very that's not going to help you in the sense of if this water level changes in the next second and becomes 17. Okay, like, you guys are going to want to know how do I write R naught such that it's in terms of H, and that's what we did here. Okay, and then from there we made that substitution and we cleaned it up. And we have now arrived at an expression that has one variable that we can derive implicitly, and our lives are very easy here. Okay, so let's do that now. Okay, that's the series of events that has gone on here. Right? These questions can be quite complicated, and they are, but they can get even more complicated if you make them more complicated. We did something smart here by switching the radius into terms of the height variable. Okay, so now we only have one variable to differentiate here. Okay, so now we can say, let's differentiate this, right? Implicit. I can never talk while writing that out. I have to concentrate on the spelling. Okay, so now let's do that. dv by dt is going to equal, you've got a whole bunch of constants here. The only thing you're really deriving is that h cubed, right? So we're going to bring the 3 down. May as well write 25 pi out front so we don't confuse anybody. And then we're going to bring the 3 down. We're going to say, okay, well, this has to be multiplied by 3h squared. Now, we were deriving, or we're looking for how the height is changing with respect to time. There is no t variable in this equation, so I need to multiply by dh by dt. Okay? Now you guys can see, hopefully, we can multiply the 3 by the 25, and we'll clean this up a little bit, and then we'll have a final expression here that we can plug in some information. We'll have 75 pi over 432 h squared dh by dt. Okay? I think the thing it's looking for, if I just go back up and look at this question, how fast is the depth of the water increasing when the water is blah blah 16 meters deep? Okay, we know what the h is now, right? That's what's great about this. This is exactly why we did this. Because it doesn't matter if I ask you 17 meters deep, 23 meters deep. You're just going to plug that value in for the h now. You're not going to have to redo all of this work over and over again to find the specific h value because you wrote it, or sorry, the specific r value because you wrote it in terms of h. That's why we did this. This is an important step here. Okay. So ultimately, we just want to isolate for dv by dt. We could get some numbers here and make our lives a little bit easier. Let's plug in. This is not easy to isolate for because it looks ugly and it's a fraction inside a fraction. So at least if we can plug in the numbers here, let's do that. Okay, so we know that the rate at the water is changing, dv by dt. We can make a little list here. dv by dt, that's going to equal 20 meters cubed per minute. That's how fast we're pouring water into this thing. And then we know h is going to equal 16 meters. And we want to know what dh by dt is. That's what we're after. Okay, we're going to come down. We're going to plug that stuff in, right? So we're going to say, okay, 20 is equal to, I don't know what 75 pi, we can type that in to get a general question here. I suppose, yeah, let's just type in the numbers. It'll be fine. Just be cognizant of the fact, I talk a lot about this in physics. Just be cognizant of the fact that when you round this, you're going to have a little bit of rounding error, right? And you just know that that's going to carry through your question. So I don't know, I might carry 3 decimal places or something here, right? 3.14 and equals divided by 432. Okay, so when I do 75 pi divided by 432, I get something like 0.547. And then I can multiply that by h squared. H is going to be 16 squared dh by dt, right? And so we could say, okay, well, 16 squared is going to be 256, right? So we're going to get, I'm doing more work than you guys maybe need, but just so we're all clear on where numbers come from and everything. And exactly, that way you guys aren't unsure as to did I round differently or anything like that. So now I can take the 256 and multiply it by 0.547. I get 140 basically, bang on. 0.0 is multiplied by dH by dt. I can now divide both sides by 140. So dH by dt is going to equal 20 divided by 140. So dH by dt will equal 1.4, and that is going to be meters per minute. Remember, this is how is the height changing with respect to time, right? Well, the water, you could say a little therefore statement, the water level okay, guys, that is a little bit more complicated. Okay, that is a harder question. In its application, I mean, the process is all still there. Okay, I would encourage you. I think the hardest questions are going to be the ones where you guys look at something and say, okay, I have a problem. This is the critical thought process that you're going to have when you sit down to start one of these questions. I have a problem with a cone. I have two variables and they're both changing with respect to time. That is the problem with this question, and that is why it gets it so much harder. There is a workaround. If we're able to write the radius with respect to the height, I then only get one variable that I can differentiate, right? And now I'm differentiating how is the height changing with respect to time, no problem, okay? If the shoe was on the other foot and I was interested in how is the radius changing as the height is changing, well, you could just rewrite the height with respect to the radius and do the exact same thing, okay? This is very, very important. You need to have the wherewithal to look at something and say, I have a problem with this question. How am I going to work around it? This is the workaround, okay? That's how you tackle cones. Cones are tricky because of this exact notion, right? Where we have two variables changing at the same time. And I showed you the workaround there, okay? So that's it for this morning stuff, okay? Again, the questions are going to be all the same. We're identifying an equation that works for the scenario, and then solving for the rate in which I'm interested in, or the question's interested in, okay? So that's an introduction to related rates, guys, this afternoon. Very similar. We're just going to see different kinds of questions, okay? So we'll see you there.